The important thing to remember about cyclohexane rings is that they are not flat. They are actually three-dimensional structures. They are not planar. And the two major conformations that they exist in are called chair conformations because they look like a chair. So, roughly like a chair anyways. So how to draw a chair? There's a couple different ways of drawing chairs. One way is to draw two sets of parallel lines, slightly offset, and then we draw another set of parallel lines here and here, and then we connect them. So that's one chair. We can draw the other chair facing the other direction. Again, two sets parallel lines, another set, and an angle. Now notice none of these lines are directly up or horizontal. There and there. So here are two chairs. Another way of drawing chairs is to draw as a V, like this, and then draw another V. Well, this one's upside down, and you draw the other V right side up, and then you connect the two. Sometimes you have to lengthen one bond. This gives you kind of a chair. These up here look better than this one. You want the other one, you can draw your V, the other V, and then connect the two, like that. What I generally do is I start off by drawing a triangle like so, then draw two parallel lines, and then connect them by another angle. And you can do it the other way as well. Regardless which way you choose, the important thing is to keep drawing them. Draw them hundreds and hundreds of times until you get so sick of drawing chairs you don't want to draw anymore, and then you draw them again and again. The only way to be good at drawing chairs is to constantly draw them. Now, it's one thing to put the chairs in. Now, the chair conformation has actually two distinct positions on it where to put groups. Each carbon has an axial position and an equatorial position. The axial positions are the ones that go straight up or straight down, and they generally follow the path of the bonds, like this carbon right here, this point. The lines going to this are going upwards, and so the axial is upwards. Here, the lines going to this point here are going downwards, so the axial is downwards. This one, lines going downwards to this carbon, down, up, up, down. Notice the axials rotate. If the up position is axial on this carbon, the adjacent carbon has a down position axial. Up, down, so on, so forth. The equatorial positions are a little bit harder to draw. They represent a position that's parallel to one of the carbon-carbon bonds. So, if the axial position on this carbon right here is up, then the equatorial position is down. Only it's not straight down, it's down at sort of an angle. See how this bond right here, it's parallel to these two bonds. The other equatorial position here, and here. These are also parallel to another bond in the ring. In this case, let me find a different color. There. In this case, this bond right here is parallel to that bond. And let me choose even a different color. Let's go for yellow. This bond right here is parallel to this bond. Okay. The other equatorial positions are here, here, and there. Okay. All the multicolors make it kind of hard to see, so I'm going to redraw that chair. And I'm going to draw the equatorial positions in. It's there, 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 there. Notice that they're alternating again. This is a down position. The movement of the pin goes downwards from the carbon to the substituent. Here it's up, up, down, up, down, up, down, and so on and so forth. Okay, now the other thing is which direction to draw. Things to notice. None of these equatorial positions actually cross the cyclohexane ring. They're all outside that ring. That's important. Other thing that's important is that none of them are straight up, straight down, or horizontal. The last thing is which direction they're going, if they're going to the left or to the right. Well, imagine there's sort of a continental divide in the ring. The ones to the right of that continental divide head to the right. So like here, it's going away, it's going away, it's going away. Things on the left-hand side also go away. See, this one's going down and to the left, this one's going up to the left, this is going down to the left, and all of these are to the left of this continental divide. So a lot of this drawing axial and equatorials is just practice. You just have to keep doing it again and again and again. Now, when it comes time to actually putting substituents on there, the substituents want to be equatorial. Axial positions are sterically demanding. Meaning, any group that's here is going to be butting heads with any group that is here, and so on and so forth. Okay, equatorial positions are not sterically demanding. Try to get your big groups in equatorial positions. Now, I mean by big groups. A big group is things like carbons and methyls. Typically, carbons are bigger than non-carbons. By non-carbons, well, I mean anything that's not a carbon. An oxygen group, a nitrogen group, a chlorine group, bromine, iodide. These atoms here are technically bigger than carbon. Okay, but the cyclohexane ring treats carbon groups as bigger groups than these because these also have longer bond lengths. So carbon treat them as bigger. Carbon, if you have a chance to put a carbon in axial equatorial or these groups in axial equatorial, choose the carbon group to be in equatorial. Other thing, branches. When you have a branch on a cyclohexane ring, here we have a case between an isopropyl group being equatorial and a butyl group being axial. But if we do the chair flip, meaning you switch from one conformation to the other chair conformation, whenever you do a chair flip, whatever is equatorial becomes axial. Whatever is axial becomes equatorial. Up still stays up, down still stays down. Like this isopropyl group is down. And down, in this case, on this chair, is axial. This butyl group is axial here, and it's down. So in the chair flip, it's still down, but instead it's equatorial. Now, in terms of which one is preferred, well, this one is the preferred structure. This one isn't. The reason why the top one is preferred is the equatorial group. Look at the carbon here. It has a branch point near the ring. Yes, this group has more carbons to it, but they are out away from the ring. This branch point is close to the ring, so you want your groups with the branch points as far from the ring as possible. These groups, bigger. So, take a look at these two structures, drawing the two chairs. Start out by drawing two chair conformations. Then we number the flat structure. 1, 2, 3, 4, 5, 6. You can number however you like. The thing is to be consistent. Here I'm numbering in a clockwise fashion. So when I number these, I need to also number in a clockwise fashion. I can choose one to go on any one. I'm going to choose one to be on the far right. And when I choose the one to be on the far right, I have to choose one to be on the far right on this chair as well. So that's one. And then counting in the clockwise fashion, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now 1 is a dash. Remember, dashes mean down. Wedges mean up. In this case, 1, this is a dash substitution on the methyl group. It's down. Down here is an equatorial position. One carbon here. Down on this carbon is an axial position. Let's clean that up just a bit. Let's make this more of a straight down. 3 position. This wedge methyl group. Wedges are up. So here we have the 3 carbon. The wedge is up here. Here, 3, equatorial. Okay, so in this case, we have a methyl group as equatorial and a methyl group as axial. Here we have a methyl group as axial, a methyl group as equatorial. Same energy. As a result, they're equal energy. They're both the same energy, so you'll have half of the chair exists as this, half of them exists as this. Let's take a look at this example right here. Again, start by drawing 2 chairs. Then we'll number the ring. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Methyl group, here, up is its wedge. It's axial here. And this one, the up position, is an equatorial position. The tert butyl group, right here, is also up. On 4, that's an equatorial position. On the 4 here, that's an axial position. Both of them, notice, are up in both cases. Here we have a methyl group as axial, tert butyl group equatorial. On the right hand one, we have a methyl group as equatorial, tert butyl group as axial. This one, on the left, is the more stable structure, because the tert butyl group is big and bulky, and tert butyl groups really hate being axial. One more thing when it comes to drawing chairs. Sometimes it's helpful when figuring out when something's axial equatorial. Let's just draw in, say, one chair conformation of this compound here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Sometimes it's helpful to just draw in the axial positions on each case. So in this case, I'm going to just draw in the axial positions. And on this one, I'm going to draw in the axial positions. Now, 1 methyl group is a wedge going up, so that's that group. 6 is a bromine going down. Here's carbon 6, bromine going down. Over here, the methyl group on 1, 2, 3, 4, 5, 6. On this one, the methyl group is going up, so we have to draw it up there. 6, the bromine's going down, to draw it down there. Okay. Now, if you do draw in the axials to help you figure out which one's axial, which one's equatorial, you have to go back and either erase these lines, because each of these are actually technically methyl groups, or go through and cap them with hydrogens. Otherwise, the answer will be an incorrect answer. The more stable one here, well, that's this one right here, the methyl group equatorial, bromine equatorial. This is the more favored structure.